now we still need to connect with the Black-Scholes equation. So for the martingale approach, it was by solving the fundamental asset pricing formula, i.e. the Q expectation. In the Black-Scholes PDE, it was fast functional manipulation. Plus solution to the heat equation, so the green function came in. Plus reversing the transformations. So actually, rather than manipulation, let's call it transformation. It's a nicer word. So here we have more things to write. Here again, we try to strive for balance between probability and PDE. Now, we saw at the beginning of this class that there was an extra connection here between martingale and PDE. And this extra connection was between the Black-Scholes PDE and the fundamental asset pricing formula, and that was via Feynman-Katz, which tells us that whether you've got a PDE or an expectation, it's the same thing. Gives you the same result. Now, let's see if we can move our binomial model and get our binomial model to produce the Black-Scholes equation. And for that one, of course, we can't use the Bernoulli model, you know, the one-period binomial model. We are going to use the real binomial model. So I see I've got a question from Deepak, but didn't we ignore O dt to the alpha terms in PDE approach as well when we do E2O? Yeah, we did, because we knew that we would shrink things enough that all we care about is a dt. Anything beyond that is too small, so we can just safely ignore it. And that's exactly why we picked delta t here when we did Taylor, is because we anticipated that as we are going to shrink delta t smaller and smaller and smaller, delta s is going to follow, shrink to become smaller and smaller and smaller, and therefore all we've got left are terms that do not matter. I mean, the rest is just really rubbish term that we'll be able to eliminate by taking the limit. So it's exactly that. So for that one, we are going to take the n-period binomial model. And the reason for that is here. So we've got something that's very coarse when we've got just the one-period binomial model. The martingale approach that we developed yesterday using stochastic calculus gives us path, gives us way to simulate this path, where you can change direction, have up move, down move very frequently. Then when we shrunk these to a local behavior, we found the PDE. PDE also tells you what's happening locally and tells you about the movement, the local movement. So we're going to try to emulate that by splitting up our tree and creating a tree of really a tree with many branches, not just one big branch, so that we have a grid inside this space. And we can, as the grid gets finer and finer and finer, we will look more and more like either this or that. We would have a finer characterization of local movement, not just one big thing for global. So that's one of the key ideas. The other key idea, which is another way of looking at things, is that if you look at it from a statistical perspective, it doesn't hurt as much as from a probabilistic perspective. When you price your option, you're going to be interested in looking at the payoff. It all depends on the payoff function, right? With the martingale approach, with the expectation that you've got. The expectation sums up, takes a weighted average of all the payoff on that line, on the expiry line. And the weights are the probabilities that these events occur. So that's the idea also behind Monte Carlo simulation. You just have enough simulation which will enable you to sample efficiently on the expiry, on the payoff line at expiry time. With the PDE, we've got local characterization up to here, and then we've got a terminal condition that covers the entire payoff line. But with the one-period binomial model, we only have 2 samples. And 2 samples is very, very, very few. So the only way to get more samples is by splitting this tree. And introducing, for example, breaking it halfway through and introducing a recombination here. And then you could even split it a little bit more finely, now in 4. And even more finely, so that you increase your number of samples on the payoff line. So that's the idea. The idea is not so much to characterize what's going on here as to sample what's going on there. But in the process, to get to many points here, we've got to fill in this space there. So now we are going to look at a big time interval t for our option. And we're going to split it into n steps of length delta t by defining delta t is equal to t divided by n. So your binomial tree, symbolically, your binomial tree will look like that. In reality, it looks morphed, a little bit warped to upwards, but that's a symbolic representation. So you've got your binomial tree, and one of the things that you can notice right away, and one of the reasons why it's a very inefficient numerical scheme, is that if you want to obtain one more sample on the payoff line, you need to introduce one more time step. So the number of samples on the payoff line are closely linked to the number of time steps. If you've got n time steps, you will have n plus 1 samples. Think about it. 1 period model, you get 2 points. 2 period model, you get 3 points. 3 period model, 4 points, etc. That's why we prefer finite difference methods for PDEs. It's because we've got, I wouldn't say a full independence, but we've got more leeway in terms of how we are going to move our delta t and our delta s. And that's something you don't get at all with the binomial tree. So the binomial tree is actually fairly inefficient, computationally speaking. Now, because we want to be consistent with the Black-Scholes model, we are going to stay or use the CR implementation. Now, it turns out that I say it now, but you will see that for most of what we're going to do next, it doesn't matter. We're only going to need to restate that. We only need really the CR at the very last step. Before that, we could do it with any binomial model. What we're going to do, we could do it with any binomial model. So it's only when we really want to converge to Black-Scholes that we're going to need that. So let's look at our recursive computation of the option price. We start at time step n. That's when we get our payoff. So we've got 1, 2, 3, 4, 5, 6, 7, 8 samples on our payoff line, meaning that we've got n is equal to 7 on this representation. And from the payoff, we will roll backwards in time. Time n minus 1, n minus 2, n minus 3. So here, k is equal to 3. All the way to 0. So that's how we navigate in time. Navigation in time. Now, navigating the state variable, the price. Well, this is node in time, this is node n minus k. We're going to call the node at the bottom 0, and we're going to go all the way up to n minus kj. That's in asset price space, all the way to n minus k. So here we do have n minus k plus 1 asset prices. So now we can identify each node uniquely with a system of time and asset price with just 2 indexes. To price the option at step n-1, so at step n-1, so time step n-1, and for an arbitrary asset price, asset node j, we're just going to use our one-period binomial model. So we'll need the price or the payoff Vnj plus 1 and the payoff Vnj. Now, to make things a little bit easier for us, we're going to use the risk-neutral implementation. This way we are dealing with the expectations, and we're just dealing with the sum of two, well, with the expected value, discounted expected value of our payoff. So just applying our one-period binomial formula, we get that Vn minus 1j, this one here, is the discounted expectation, expected payoff, where the probability weights are p star for the up move, 1 minus p star for the down move, and we've got two payoff, Vnj plus 1 and Vnj. So we can do something a bit better with respect to the payoff. If we're trying to price a call option, we could really put maximum of the stock price and minus the exercise price or 0 here and there. Now the question is, at expiry on node nj plus 1, what's the stock price? And same thing, what's the stock price there? And that's actually fairly, well, that's actually very easy. If you think about it, look at a path for S and J. So a path for S that would lead it to S and J. It turns out that these paths are of course not unique. To land here, S could have also gone here and there, or like this, or like that. But we don't care about how it got there, not at the moment, at least. We care about its value. And for the value, it's actually quite simple. This is S and 0. Just look at the two extremes. This is S and N, right? These are the two extremes. For these two, you only have a single path that leads here and there. This is all the way down across n steps. So that means that you went down n times and 0 times up. And this one is all the way up over n steps, meaning you went up n times and down 0 times. So the stock price here is S0 UN D n minus n, right? And the price there is S0 U0 D n, which means that SNJ should be S0 Uj. So the index here that tells us how tall we are in the tree tell us actually how many times we went up. And if we don't go up, we've got to go down. So the index, the number of times we went down is n minus j. And you can check that. If you're here, well, you've gone down n minus 1 time and up once. So Sn1 is indeed S0 U1 D n minus 1. So now we know exactly what the terminal prices are over there. So we can compute our formula exactly. Now, what's more fun than a 1-period model? A 2-period model. So what we're going to do, and then we take a break, what we're going to do is say, okay, we've got a formula that works for a 1-period model, but we knew that from the beginning. So in order to entertain ourselves, let's try to see if we can find a formula, one formula for a 2-period model. How does it work? And then from there, we can expand it to an n-period model and having just one formula in one line that tells us today that's the price for an entire, for a call option given an entire tree, but I just want one formula. I don't want a recursion. I don't want an algorithm. I just want a clean thing on one line. Can we do that? Have you already done that? No. Do you think we can do that? Yes. Are we going to do that? Oh, yes. Don't even let you answer. So to price an option at step n minus 2, we're now here, meaning that we will look at essentially 3 terminal prices. So Vnj, Vnj plus 1, and Vnj plus 2. Remember, if you've got n steps, you've got n plus 1 evaluation point, you've got 2 steps here, so that means you've got 3 evaluation points, 3 samples here. So how are we going to get a formula for a 2-step process? Well, let's start with the formula for the 1-step process. So let's compute Vn minus 1j, Vn minus 2j as a function of these two. Vn minus 1j and Vn minus 1j plus 1. And that is easy. We can do that. It's just a 1-period binomial model again. So Vn minus 2j in terms of the next 2 nodes, which are Vn minus 1 j plus 1 and Vn minus 1 j. And ignoring, for now, the endpoints, is just the discounted expected value of our option at these 2 nodes. But then we know what this is and we know what that is, right? Because we have already calculated that using our 1-step formula. So let's just plug the values here and there and see what happens. So I've got Vn minus 2j is equal to d p star. Let's give it some colors. Vn minus 1 j plus 1 plus 1 minus p star. Vn minus 1 j. So we're going to plug in the one-period binomial model so that now we've got a formula that is directly in terms of the payoff at time n. So that's D multiplied by P star. This green thing is actually equal to D multiplied, green thing. Green thing goes with green. D multiplied by P star V n j plus 2 plus 1 minus P star V n j plus 1. Now we look at the second term, plus 1 minus P star multiplied by the black thing. When you plug in the one-period binomial model binomial formula into that, you get D multiplied by P star V n j plus 1 plus 1 minus P star V n j. Spring cleaning time. I can take out the D's. So I get D squared multiplied by, let's count the terms. I've got a V n j plus 2. I got 2 V n j plus 1. And I've got a V n j. The 2 V n j plus 2 are P star, the V n j plus 2, sorry, has a P star square in front. So let's write it. P star squared V n j plus 2. Then I've got 2 times P star 1 minus P star, 1 minus P star, P star. So plus 2 P star 1 minus P star V n j, V n j plus 1. And then finally, I've got 1 minus P star times 1 minus P star. So plus 1 minus P star squared V n j. And we've got one formula for a two-period binomial model. And we've got something interesting. We've got P star squared here, 2 P star, 1 minus P star there, and 1 minus P star squared there. I wonder what this might mean. Let's have a look. We got a two-period binomial model here. We've got V n j plus 2 here, V n j plus 1 there, V n j here, and we've got V n minus 2j here. Now, starting here, what's the probability that I will end up there? Well, I need to go up twice. I go up with probability P star. So the probability that I'm going to end up there is P star squared. One up move with probability P star, and then independently a second up move with probability P star. Similarly, what's the probability that I will end up there? Down there. Well, one first move with probability 1 minus P star, and then independently a second down move with probability 1 minus P star, so that's 1 minus P star squared. And then finally, how am I going to get here? Well, I've got two ways of doing it. First one is one up move followed independently by a down move. That has probability P star 1 minus P star. And then the other way of getting there is one down move followed by one up move. So I've got 2 times P star times 1 minus P star. So now what we see emerging out of the Bernoulli probabilities are really the binomial probabilities complete with your binomial expansion. This really hints at the binomial expansion. Coefficient 1, coefficient 2, coefficient 1. That's the dreaded CNKs. You remember from your permutation combination days where you've got the CNKs, which are the number of ways you can pick k objects from a bag of n objects when the order doesn't matter. That's also known as Pascal's triangle, except that Pascal didn't invent it. He actually stole it from some Song Dynasty Chinese mathematician. That's a case where our mathematicians in the West were not immune to doing a bit of industrial espionage at times. So that really hints at this binomial development, which means that rather than writing the long formula, we could compress it using our good old friends, the number of combinations. And so our formula, Vn minus 2j is equal to p star squared Vn j plus 2 plus 2 p star 1 minus p star Vn j plus 1 plus 1 minus p star squared Vn j can be written much more compactly as, oh, I forgot the d squared. I forgot my discounting. I forgot the interest rate. D squared times the sum from I equals 0 to 2 of the C2i's, knowing that C20 is 1 and C22 is 1. So C2i, P star I, 1 minus P star 2 minus I, and then we've got the payoff function. Now, that's a more compressed way of writing that. And that's actually quite helpful because now we can say, OK, if it works for 2 times steps, maybe if I replace the 2 by a 3, that works for 3 times steps. Maybe if I replace the 2 by a 4, it still works, etc. Maybe if I replace the 2 by a n, I get discounted in times, a sum across n possibilities. All these are my binomial probabilities and then my payoff. So once we are there, our intuition says that we could go a lot further and that this formula should still work at step n minus k. So of course, we would need to prove it, but we're not going to do that. That's in the notes. We're just going to speed up time. Now, in the past nanoseconds, we've proved that it actually works, and now we can use the formula directly. It's very nice when you can speed up time, right? So that's going to be our starting point after the break. We're going to look at that and see if we can see Black-Scholes here. I can see it from this angle. Now, if I move, I don't see it anymore. But if I see it from this angle, you can start to detect some traces of Black-Scholes. Not directly, but almost. So 10 minutes break, and then we transform that into the Black-Scholes equation.